Identify the absolute extrema and relative extrema of the function f of x equals x to the third plus x squared over 6 within the interval x between -8 and 1, including the endpoints. Critical points and singular points are candidate points for finding maximum and minimum. In order to find critical points and singular points, we begin with the first derivative of the function. This is a relatively easy function to differentiate. Just use the power rule. First, we bring down the power of a third to be a coefficient, so 1/3 x, and then subtract the power by 1, -2/3, plus 2/6 x to the 1. Let's simplify that 2/6 to become a 1/3. With these types of min and max questions, because we'll be doing more work with the first derivative, finding critical points and singular points, it's better to factor and simplify the first derivative to make our work easier later. The negative power and fractional power are a bit tricky. Just remember that negative power means to reciprocate, and fractional power means a root. In this case, we have x to the -2/3. That x, originally in the numerator with a negative power, tells us to put that term in the denominator. The 1/3 power means that we're going to have a cube root, and the 2 just means a square. There are multiple ways of expressing x to the -2/3. In either case, this factor is in the denominator, but we can have the cube root enveloping the x squared, or we can have the square of that entire cube root. So it doesn't really matter which way you pick. To find critical points, we set the first derivative to 0 because we're going to be solving for x now. This is the reason why we needed to factor the first derivative. It's easier to solve. Setting the first derivative to 0, and I've put in this restriction because we have x in the denominator and we can't divide by 0. Then multiplying both sides by cube root of x squared and multiplying both sides by 3, we're going to isolate that numerator, 1 plus x to the 5/3. And solving for x to the 5/3 equals -1, x equals -1. At a singular point, the first derivative is undefined. Our first derivative in this case is a fraction, and fractions are undefined when we divide by 0. Therefore, x equals 0 is a singular point. On a number line, we plot any critical and singular points that we find, and analyze the sign on the first derivative. The 1/3 is just a coefficient, doesn't do much. The denominator, we have an x squared. The denominator will always be positive. The numerator, however, will change depending on where you are in the interval of x. There are a few ways to do sign analysis. We can plug in test values of x into the first derivative and see what sign we get, or just try to rationalize the relative, which number is bigger, which number is smaller. Test values are tougher to use in this case because of that awkward power 5/3. It's a bit tougher to put in test values and having to compute that. What if we just imagine a very negative number, like negative a bazillion? Negative a bazillion to the 5/3, because 5 and 3 are both odd numbers, we're going to have a negative number as a result. And 5/3 is a number that's bigger than 1, which means that this negative number will get even bigger in magnitude. 1 plus a really big negative number will give us a really big negative number. Therefore, the numerator is going to be negative for x less than -1. Between -1 and 0, x will be a fraction that's less than 1 in magnitude, say 0.5. In this case, it's going to be -0.5. So if we have something that's like 0.5 in magnitude and then raise that to a power that's greater than 1, overall, we're just going to get a smaller result. Within this interval, x to the 5/3 will be a negative number, but small in magnitude, smaller than 1. 1 plus a smaller negative number will give us overall a positive sum. And for x greater than 0, a positive number raised to 5/3 will still give us a positive number. Adding 1 to it just makes it 1 bigger. Therefore, the numerator will be positive in this interval. Let's assign these intervals of increase and decrease on the number line. When the first derivative is negative, the function is decreasing, and when the derivative is positive, the function is increasing. Notice that the function decreases and then increases according to the first derivative test. We have a minimum point at x equals -1. At x equals 0, the function increases before 0 and then increases some more after 0. This is neither a minimum nor a maximum. The question asks us to find the relative and absolute minimum maximum within a bounded interval, which means that we have to evaluate the value of the function itself at the endpoints and also at any min or max points that we found using sign analysis. At the endpoint x equals -8, put in -8 into the original function, not the first derivative. We interpret that power of a third as a cube root, and the cube root asks us what 3 of the same numbers multiplied together gives us the stuff in that cube root, in this case the -8. 8? The answer is -2. -8 squared, which is 64, and then divide by 6. Let's simplify that fraction. Divide top and bottom by 2. We have 32 over 3. Remember adding and subtracting fractions from elementary school? In order to add and subtract fractions, we have to have the same common denominator. We have a 32 over 3. Let's turn that 2 into something over 3. In this case, it will be a 6 over 3. And we can check. 6 divided by 3 is 2. So in fact, that is the correct equivalent fraction. We have -6 plus 32, which is 26 over 3. At x equals -1, the critical point, which is the minimum, we have -1 to the power of a third plus -1 squared over 6. -1 to the power of a third, that's -1. The -1 squared gets rid of that negative, so 1 over 6. The -1 becomes a -6 over 6, and we add that to 1 over 6. -6 plus 1, -5 over 6. At the other endpoint, x equals 1, we have 1 to the third root plus 1 squared over 6, and that's 7 over 6. Most of these numbers here are over 6, except for this 26 over 3. How about we multiply top and bottom by 2 so that we have something over 6, which makes it easier to compare. All of these values are over 6. We can just compare the numerator. 52 is the most positive number. Therefore, we have a maximum, not just a relative maximum, but the absolute maximum within this interval. X equals -1 is the location of a local minimum, and in this case, it's the most negative value of the function. Therefore, the absolute minimum of the function f of x occurs at -1, and the value of the function is -5 over 6. At the other endpoint, this is neither a minimum nor a maximum. It's just another point on the function.